Hello boys and girls, welcome to your next lesson. To start you off, we are just going to revisit some of the stuff we did in the previous lesson. Give yourself 5 minutes just to pause the video and have a go at answering these questions. Okay, so this is what you should have got in your answers, and you will remember that when a substance is heated up, think back to your energy topic. It's the thermal energy that's being used to break bonds between particles. Think about when you heat a solid. So number 2, it melts. It goes from a solid to a liquid form because you're breaking the bonds. When you heat a liquid, it boils or evaporates. We'll discuss that in a bit more detail next lesson. But it boils and it forms a gas. Again, you're breaking bonds because you're heating the object. When a substance is cooled, the thermal energy is being lost and you make bonds. You form bonds between the particles during this change of state. When you cool down a gas, it condenses and forms a liquid. Think about the shower room. There's condensation on the windows and the mirrors when the steam turns to a liquid. When you cool down a liquid, it freezes and becomes a solid. Think about putting water, liquid water in a freezer. It freezes, it becomes a solid, you're forming bonds. From last lesson, the equation for density is density equals mass divided by volume. You can either have the symbol formula there, where the P type thing is not P, it's rho. It stands for density equals mass divided by volume, or rho equals m over v. And number 8, solids are most dense because they have more mass in the same amount of volume. Remember, density is mass per volume. So if we're comparing things with the same volume, the things with the most mass in them are the most dense. Okay, so from your fact book, you will remember and you'll have read this lesson's about internal energy, and these are the 6 points we'll be focusing on. The internal energy of a substance is the energy caused by its particles' position and their motions. We'll be looking at the equation for internal energy. We'll be thinking about the force of attractions between particles, and we've talked a little bit about this in detail in the previous lesson, so I won't go into too many details this time around. When a substance heats up, we'll be talking about its kinetic energy of the particles and the energy of the particles, the potential energy when substances change state. And we'll be looking at a heating curve, temperature time graph. So let's go straight into it. Let's think about the energy of particles. There's 4 particles on the screen, yellow ones. They represent particles in a solid. You can tell they're part of a solid because they're in a regular pattern, neat rows, and they're all touching, compact together. We know those particles can't just move about wherever they want. They have tight formation, strong intermolecular forces, and they can only vibrate around a fixed position. What might happen to the motion of these particles if we were to heat up the object? Pause the video, give yourself a minute to think about it, and let's see if you get it right. Here's the same 4 particles. This time we're heating the object up. You should have thought that the particles began to vibrate faster. They absorb the extra thermal energy that we put in when we're heating, and they vibrate faster about their fixed positions. So heating an object causes the particles to vibrate faster in a solid and move faster in a liquid and a gas. The energy in an object is stored by its particles. So this topic we're looking at something called internal energy. The word internal means inside. So we're not looking at the object itself, we're thinking about the particles, the atoms and the molecules that make up the object, and we'll be looking at the energy stored in those particles. So we're looking now at a molecular level, atomic level, particle level. Kinetic energy of the particles. So again, we're not thinking about the whole object. For example, we're not thinking about a football if we're thinking of a solid, we're not thinking of the football, we're thinking of the atoms and the particles that make up the football. When that football is laying on the ground, the football itself doesn't have kinetic energy, but the particles inside it are always vibrating, or they're always moving around. This means that the particles have energy in their kinetic energy stores. The football itself doesn't, the particles do. The faster those particles move, the greater the kinetic energy store is. And we've seen from the previous screen, we can increase the kinetic energy of particles by increasing the temperature, by heating them. Particles also have potential energy. So there are two types of energy that particles have: kinetic, due to their motion, and they have potential energy. The potential energy is due to their position in relation to each other and their intermolecular forces. So the way that the particles are held together in an object gives them the potential energy. When particles begin to move further apart, their potential energy increases. So it's important we realize that we're talking about the particle's energy, not the object's energy in this case. And there are two main types, kinetic and potential. So the total energy that particles in a system, remember a system is an object or a group of objects, total energy in of the particles in a system is equal to the sum of the kinetic and potential energy stores. We can summarize that with an equation. Internal energy equals the kinetic energy of its particles plus the potential energy of its particles. Please pause the video and copy that down. That's an important equation. If you haven't done so already, please copy these slides down also. Okay, let's think about heating up the system. When we heat up a system, an object or group of objects, we transfer energy to its particles. The energy comes from perhaps the chemical energy store, if it's a fuel that we're using to heat up, or it could come from electrical transfer. Heating is a transfer system that transfers energy to the particles. The particles gain energy in their kinetic energy stores. So the transfer happens by heating, and the energy gets transferred into the particle's kinetic energy store. This causes the object's temperature to rise. And the temperature rises because the particles in the object or system have gained kinetic energy, they're moving faster, temperature rises. Eventually, if we keep pumping in this energy, the particles gain enough energy now to overcome the intermolecular forces that are holding them together. So now, because they're moving further apart, the bonds are breaking, their potential energy increases. It's important we realize that the temperature at this point no longer rises, even though we're still heating the object up. The temperature doesn't rise, the object changes state. Stop the video and copy this down, please. Let's just take a moment to think about specific heat capacity. We've come across this in the energy topic, and it's important here because if you remember the definition for specific heat capacity, it's the amount of energy needed to raise the temperature of 1 kilo of something by 1 degree Celsius. So in this scenario, we're heating something up. We're raising its temperature. Because we're raising its temperature, we know that the temperature change depends on the mass of the substance, how much there is, the specific heat capacity of the substance. Different substances have different specific heat capacities, and the size of the energy input, how much energy we put into the system. This is specific heat capacity, and just a reminder of the formula there. If you can't remember it, please do copy this down. It's given to you in the formula sheet, but you do have to realize what the symbols stand for, and you'll be expected to use this formula. Take a moment to copy the slide out before we move on. So let's take a moment here, a progress check, see how you got on. pause the video. This should take you about 10 minutes. I'd like you to answer these questions based on what we've done. You can rewind the video if you need to have a look. Please pause the video and we'll go through the answers in a second. Okay, so this is what you should have got answers-wise. The particles begin to vibrate or move around. We know that the kinetic energy store of particles, when the particles have that kinetic energy store, they vibrate or move around. The greater the kinetic energy, the faster they move around or vibrate. Number 2 was, what is the potential energy store of the particles due to? It's due to their position relative to each other, and it's caused by intermolecular forces. Number 3, system's total energy is called the internal energy. And remember, it's the sum of the kinetic and potential energies of the system, of the particles, sorry. What could you do to an object to raise its internal energy? Well, you can heat it up. This causes particles to vibrate or move faster, so it increases kinetic energy. And later on, if they have enough energy, we can increase the potential energy part of it by causing the particles to move further apart. What occurs if you heat a system enough to break the bonds? A change of state. We might get melting, or we might get boiling. We're talking about heating, so they're the only 2 changes of state that can happen due to heating. Number 6 and 7 were challenge. Why the internal energy of particles in a gas is only due to the kinetic store? Well, think about it. In a gas, we have very, very, very little intermolecular forces. They're negligible. So we can think of it, we can say that the energy is due to just the motion of the gas particles. So that's the kinetic energy. And which state would need a larger amount of energy change, melting or boiling? It'll be boiling. We need to completely overcome the intermolecular forces when we go from a liquid to a gas, whereas solid to a liquid, we just have to slightly overcome them. Here is a what we call a heating curve. It's temperature against time. Please copy this out. I'd like you to do this large in size so we can fill it in. So what we get here is different states. So we can see that as the temperature increases, A, D, and G, the temperature is increasing over time. B and E, temperature does not rise. So this is what happens. When we're heating, the yellows, heating a solid, liquid, and gas, we're getting a temperature increase. At the flat parts, we're getting no temperature change over time, but we are getting a change of state, melting. And the second one is my mistake. I should have said boiling at the top there. Please bear in mind this one here is boiling near the top between liquid and gas. Here's your final exam question. Please have a go at this. Okay, so for question 1, we had the particles in a gas moving around. Describe the movement, range of speeds, the random speeds in random directions. Part B, the tick was internal energy, due to the kinetic and potential. C, the equation for density equals mass divided by volume. And the calculation there is the mass is 0.00254 divided by the volume of 0.0141 gives you 0.18 for 1 mark, and the kilograms per meter cubed as your answer for unit. Question 2, we've got the answers here. I'm not going to go through them, but please take a moment to check your answers, see if they're correct. If they're not correct, please go back and correct them. And to summarize, from the fact book, we've gone over the idea that internal energy is energy caused by the particle's position and motion in an object. We know the equation now, internal energy equals kinetic energy of particles plus potential energy of particles. We've talked about in the last lesson, forces of attraction between particles are very strong in a solid, they're weaker in liquid, and there's negligible forces in a gas. When a substance heats up, kinetic energy of the particles increases. When they change state, the potential energy increases, and we've seen a temperature time graph to see what happens on the flat parts change of state. Thanks, guys.